Hello, Rebecca. Welcome back. Today we are gonna finish out the last part of 1.2. We've been talking about the nucleus, and today we're going to talk about mass spectra. So this is kind of one of the techniques that chemists will use to determine the isotopes that they find in a sample. And then at the end, I'll have you do some review and you'll do a concept map like you did for 1.1. So let's look at this question. Why is it that argon has a larger relative atomic mass than potassium, even though it appears beforehand in the periodic table? So I give you a picture, right? You can see potassium's over here, argon's over here, and then we have their relative atomic masses, which you could also find on the periodic table. Why is argon heavier, right? So take a second to think about that. Think about what we learned last week. Pause the video, write down your answer, and then I'll talk about it. Okay, so this basically means that argon must have a greater proportion of heavier isotopes than potassium. So let's say argon's heaviest isotope is argon 40, and let's say that that is its most abundant, and potassium has isotopes like potassium 39 and like 37, and those are more abundant than its heavier ones. It just means that for whatever reason, those isotopes are the most abundant and form the most often for argon, so it ends up having a bigger mass. So we will see trends in atomic mass in the periodic table. We're going to talk about that in a little bit, but sometimes you get these weird things like this that happens where potassium, even though it has an extra proton, actually weighs less most of the time than argon. So let's think about this picture for a second. This is kind of an analogy to help us think about how a mass spectrometer works. So we've got this ramp here, right? And we have 3 different balls, and we have a blow dryer. And the question is, which ball would be deflected the most as it rolls down the slope? So you can assume this is just like a straight slope, right? There's no weird angle to it. These balls, if the blower wasn't on, would just go straight down and hit the 0 point. But when this blower is turned on, each of them will move, right, in this direction. And the question is, which ball will be deflected the most? I don't actually know what this is, but we're going to say this has the most mass. So this would have the most mass, this would have the least mass. So take a second to think about that and write down your answer. Okay, so the ball with the least amount of mass, the ping pong ball, it will be deflected the most, right? The flow of air will be able to move it more than the heavier ball, right? It's easier to think about this if you think of like something really heavy like a bowling ball or something. But the ping pong ball will probably be deflected completely over to 5. The golf ball will be deflected somewhere in the middle, and then this last ball will not deflect very much at all. Because this ball has a lot of mass, it's hard to move. This ball does not have very much mass, so it moves a lot. You just need a little bit of force to move it a lot. So the key difference here and how much they move is their mass, right? So this is the key property that mass spectrometers use as well. And I'm going to have you watch a short little video that describes how they work.
For a sample of chlorine gas, we can estimate that 75% of the atoms would be chlorine 35 and the remaining 25% would be chlorine 37. These different forms of an element are known as isotopes. All isotopes of an element have the same number of protons, but a slightly different number of neutrons. This concept of isotopes was actually discovered using an analytical technique known as mass spectrometry. For chemical research, the pharmaceutical industry, and in forensic science, there are many techniques and tests to identify a synthesized compound or a sample obtained from a crime scene. One crucial technique is calculating the molecular mass of a compound or a sample. This can be done using a mass spectrometer. The beauty of mass spectrometry is that only a very small sample is required. This is important when only a small sample is made or if the evidence is only present in minute amounts. A sample must first be vaporized. Once this is done, the vaporized sample is then bombarded with a beam of electrons. This beam of electrons knocks off electrons from the molecules which make up the sample, creating positively charged ions. This process is known as ionization. The ions formed usually have a +1 or a +2 charge. These ions are then accelerated in an electric field before being deflected by a magnetic field. The pattern of deflection according to charge and mass can then be depicted on a spectrum. The main idea here is that ions with a large mass to charge ratio, meaning a large mass and a small charge, are deflected less than ions with a smaller mass to charge ratio. When this was done using a sample of neon, the resulting pattern of deflection showed that 3 isotopes of neon existed: neon 20, neon 21, and neon 22. The positions of the peaks on the spectrum will tell you the mass of those ions. Besides showing the existence of these isotopes, the isotopic abundance can also be determined from the mass spectrum. The height or the intensity of a given peak tells you the relative abundance. So when a crime scene investigator gives the lab even a small fleck of a white powder, its molecular mass can help identify what it is. In summary, mass spectrometry is an analytical technique used to determine the molecular mass of a compound and indirectly helped to prove the existence of isotopes.
So, scroll back here to a picture I'll talk about there. So we can see a lot of words that we've been learning about, like ion, and we heard isotope, right? The sample goes in, a bunch of electrons are shot at the sample, which creates ions, right? These ions go through the machine. There's a magnet here that deflects them because they are positively charged. And like in that first picture, the more massive it is, the less it will get deflected, right? And the less massive it is, the more it'll get deflected. Just like the ping pong ball versus the golf ball. And these machines are used in lots of labs. Pretty much anywhere you're doing chemistry, you'll see one of these. They even have these in airports. That's how they test for different things that they find in people's suitcases if they think they're suspicious, because there are whole libraries of mass spectrometry data that corresponds to different things and different compounds. So this can be a really useful tool when you're doing chemistry.